Hello students, welcome back to another lecture on classical mechanics, and today's class will be the lecture number 7. In the last class we have seen how to classify dynamical systems into holonomic systems and non-holonomic systems, and we have also seen what is the advantage of knowing the constraints. The constraints are ultimately going to help you to reduce the number of equations to be solved. That is the purpose of constraint. And constraint also give difficulties. That's why we have made some classification, holonomic and non-holonomic. So today we'll see how to write down formally. Formally means how to express the constraint in the form of an equation. Okay. So if you are going to, let me therefore write down that we have f being a mathematical function. It could be any function. F is a function of generalized coordinates, for example q, and then you have comma t. If you are going to write down like this, then it means that I have an equation. So you need to understand what do you mean by this. This means I have an equation containing the generalized coordinates and time. That's the meaning. And this is what is known as the equation of constraint. So what I said was formal representation. This is how we write formally. In particular, you can always write down certain expression. For example, in the case of the simple pendulum, what did you write in the last class is, we have written down x square plus y square equal to L square would be the equation of constraint. But the appearance of this second equation, namely x square plus y square equal to L square, and the one that is written above, namely the formal representation, looks somewhat different. Initially, it appears like that. It is not different actually. It is going to be the same. So, in order to understand how this is written clearly, this x is one of the variables. So, we say that this is q1 because x comma y is very particular about Cartesian system. You don't use x and y in polar. So, therefore, you should remember that our generalized representation or the formal way of writing down things will be in terms of generalized speed, generalized momentum, generalized coordinates. And therefore, x, y will not have any special significance. Therefore, we will rename. X will be renamed to q1, y will be renamed to q2. And of course, L is a constant, that's fine. So you can say that that is just a constant, C. And therefore, what happens is, since we are going to have two of the variables required, the system is naturally a two-dimensional system in this particular case. And therefore, we will be writing that f of q1, q2, t will be equal to 0. So, for the case of the simple pendulum, the general representation will look like this. So, even though q is written here, so this q here actually, the meaning implied by q is the set of all q's. So that is how you have to understand. So this is not a single q, but this is the set of all q's required. It depends on system to system. If you want 23 or 24 coordinates, for example, you'll have to write down 24 of them. q1, q2, q3, etc. up to q24. That's what I mean to say. So in the case of the simple pendulum, you have q1, q2. And t, as I already told you, that this is possibly. So sometimes t will be explicitly present, sometimes it may not. So in our case of simple pendulum, this t was absent. So since t is absent in our case, we will be writing that f of q1, q2 would be equal to 0. So this is what we say the formal way of writing down the equation of the constraint corresponding to the simple pendulum case in this particular case. And as you see that this particular constant c need not be written down here. F of q1, q2 is equal to 0 means any constant may be there, any constant may not be there. So this is more general. You should remember that f of q1, q2 is more general when compared to x square plus y square equal to L square. So you should remember once again, if you are telling the thing in a reverse way, we can say that x square plus y square equal to L square is a very specific example of the more general way of writing f of q1 comma q2 equal to 0. So you should at least now in a position to appreciate how we move forward from specific case to general case. Simple pendulum is only a specific case. We cannot every time write the equation for simple pendulum only. We must be able to generalize to any dynamical system. So this arrow that I have written here represents that we will move away from simple pendulum and go to any other system. That any other system is what is known as more general system. And we will classify a situation where time doesn't appear explicitly. And therefore, if you write like this, that means let me express it with more number of coordinates, f of q1 comma q2 comma q3 comma etc. It depends upon whatever system that you have. If you need n coordinates for them, then all n of them should be written. The most comprehensive way of writing q1, q2, q3 etc. will be to write just a single q. Here you see only a single q. The meaning of a single q here without suffix. Single q means, remember, suffix is not there. Here you see suffix is there. 1, 2, 3 suffixes are there. So if the suffix is absent, it means that you will have to expand it to that many number of q's as required. So if you want to be very specific and explicitly write that, then we can write like this. F of q1 comma q2 comma q3 etc. up to n, where n represents the number of degrees of freedom. So this is how the equation of constraint will be written. And since t is not at all visible here, it also happens to be an holonomic system. So therefore I will write down that this particular equation is valid, or it is written for the holonomic system. Because the equation is an equality with equal to 0 is written because of that reason. And fine, time is also absent. Okay, proper classification we have seen, but now I would like to emphasize the notation with f of. Okay, f of q1, q2 etc. equal to 0 is the generic or the most general way of writing down the equation of constraint. So this is the first point. Second point is, if this is the equation of constraint corresponding to the holonomic system, how do you write? How do you write it for the case of non-holonomic system? So if you are going to move from here to the non-holonomic system, then how do you write this? This is quite simple, that you already know what is the reason. Non-holonomic systems will be such that the equality relations are not there. Equality relation is not there means instead of that you may be having inequality relation. So we simply write down formally like this: f of q1 comma q2 comma etc. until n number of coordinates, that is n number of degrees of freedom, will be something like greater than or equal to 0. So it can be greater than or equal to, or it can be less than or equal to. So, okay. So inequality. Equality should not be there means inequality can be there. So if you have an inequality relation like this, then this relation will be the equation of constraint for non-holonomic system. This is one possibility. This is not the only possibility, but this is one possibility. What is another possibility for a non-holonomic system? The non-holonomic system, another possibility is that you may be having derivatives or velocities. If velocities are going to be involved into the equation, then they are also non-holonomic. Therefore, I will write down that instead of this kind of an equation, you can have another equation where velocities will enter into picture. So let us first of all finish the coordinates q1 comma q2 comma etc. up to qn. Of course, there is a comma here. Then comma, you also have possibly derivatives, that is time derivatives of q. So probably q1 dot, q2 dot etc. They are also dependent on this. If you are going to say that the equation of constraint depends on the velocity, that means this q dot, or it may be depending on this velocity q2 dot etc. If at all any velocity dependent is entering into picture, then this equation is the one corresponding to the non-holonomic system. So this is also non-holonomic system. But remember, there is an equality is there. So whether the equality is there on the right hand side or inequality is there, it doesn't matter. The moment this time derivatives enter into the picture, this becomes non-holonomic system. So this is how you can classify. That means you can see what is the difference between the equation number 1 and how much difference is there between equation 1 and 2. And again, if you compare equation 1, 2 and 3, what are the possible differences? You must be able to distinguish between the features seen in equation 1, 2 and 3. So based on the appearance of the equation, you must be able to tell whether the system is holonomic or not. That means we are not going to explain everything in terms of English, but we are interested in writing down in a formal mathematical way. That's what I mean to say formal. Formal means the mathematical way of writing down the general equation for holonomic and non-holonomic system. So for non-holonomic system, two options are there. It can be an inequality or that the time derivatives can be present. That is what I mean to say. This is first point. Second important point that I would like to express is when there are no suffixes are present, only q is there. Suffix is not there. It means I'll put this is equivalent to the set of all q's. That means q1, q2. If you are going to have n number of coordinates required to specify the system, then the number of degrees of freedom is n. So the q is the shorthand notation or shorthand representation for the set of all q's. So for the first time when you are learning, it will be comfortable that you explicitly write down q1, q2, q3, etc., qn. And once you understand that there are n number of variables are present for a given physical system, then instead of writing every time q1, q2, etc., you simply write q. Okay, so this notation, what is an advantage of this notation? That is very important because the meaning is that I can write down f of q1, q2, etc. up to qn equal to 0 can be written in a shorthand representation as f of q equal to 0. These two are same. So you can see the advantage, you need not write so many things. So therefore, q doesn't mean a single q. That is what I wanted to tell. Q doesn't mean single q. Rather, it means the set of all q's for a given system. Okay, it can be it can be 2 q's or 3 q's or 300 q's. Whatever number, that many number for a given physical system that you will have to expand. That's the meaning. So now we have seen equation 1, equation 2 and equation 3. They are the formal way of writing down the equation of constraint, and based on that itself you can tell whether the equation that you have written corresponds to the holonomic system or a non-holonomic system. So let us see one simple example. Suppose if you ask the question, there is an object that is sliding down an inclined plane, but the inclined plane is not a smooth one. It has some kind of rough surface. It is not very smooth. Okay, so which means that coefficient of friction is not 0. That is what I mean to say. Some roughness is there. It may be small or big. The purpose of the roughness is to avoid the slipping. So the without slipping I have given in order to emphasize that without slipping. So that is the meaning of rough here. If it is not rough, then basically it will slide and come down. Okay, without any dissipation. So the slipping is absent means you are going to have some roughness in a surface, but even then you can slide down. So you can easily imagine the usual everyday life that you keep a big stone like this where the surface is rough surface. You have a rough surface here. Even then this particular block will come down because of gravity. It will slide down here. Okay, sliding down is different and slipping is different. Slipping means where if you completely remove all the friction, for example, using the very smooth surface and then a little bit of lubrication and all that, then you will be having slipping. That means smoothly it will not fall down. Some kind of jerk may be there. That is when the slipping takes place. Okay, if the jerks are absent, then we say that slipping is not there. smooth sliding will be there. So I am trying to distinguish between sliding and slipping. Okay, so these points are very important because you'll have to catch these words in order to make a decision whether it is a holonomic system or non-holonomic system. So what is the question now? The question is simple one. You are having an object which is sliding down an inclined plane, but the plane is slightly rough surface so that no slipping takes place. Now, will you classify what is your idea? What are you going to do now? Is it coming under holonomic constraint, or will you classify it into non-holonomic constraint? Because constraint is there, that is clear. The object has to slide down the inclined plane only. It cannot fly. So there is some restriction. So constraint is there. What type of constraint it is? Okay, is it holonomic or non-holonomic? That's our main question. So the answer is that this will be coming under the non-holonomic system. So let me write down that this is non-holonomic constraint. So naturally, you need to explain why do you say that the constraint is non-holonomic? Is because we do not have certain thing with us. Non-holonomic means it can be due to several reasons. One of the reason is velocity dependent. The second reason is you may not have the equation of constraint at all. If the equation of the constraint itself is not there, naturally it is non-holonomic system. So in the second example, we have an object rolling down. This time it is rolling instead of sliding. So there is a difference here. So this time the object is now rolling down an inclined plane. Once again, it is without slipping. So of course, without slipping is the one that is going to give you an hint that some kind of frictional force is present. And then this time it is rolling down an inclined plane rather than sliding down. So you can consider something like a sphere which is rolling down an inclined plane. So that's a kind of situation. Now in this particular case also, of course, there is no big difference between the first and second example. Now as far as classification is concerned, you will straight away write down that this is non-holonomic. But that classification is somewhat easy. But however, if you ask a specific question, for example, why is it non-holonomic? Due to what reason? So you should also provide, okay, classification is correct, non-holonomic, because frictional forces are involved and you do not know the equation for that force, etc. But however, there is a big difference between the previous example and this present example number 2. And the reason is that additional reason over and above this is the following. That when a particular thing is rolling down, suppose maybe that if you want to have some kind of a diagram, you can draw like this. And suppose if you are asking the question why it is so, then remember one thing, that the point where you have a contact here. So this is the point of contact, right? So this is the point of contact. That means contact between the sphere and the inclined plane. There is only one point of contact. All other points will be not in contact with the inclined plane. Okay, because this is a spherical object, there will be only the bottom portion which is touching the plane, only that will be in contact. All other portion will be not in contact. Okay, so that point of contact, is it sliding or is it slipping? So the question is clearly given that it is not slipping, and therefore that is a reason that is going to you are going to write that reason, that the point of contact of the sliding object. So okay, let us say that of the sliding of the so in this case we will say that this is a rolling object. Point of contact of the rolling object is stationary. So even though it is rolling down, fine. So this is rolling down like this, and then it is coming down the inclined plane. Even then, even though it is continuously rolling, when you take every snapshot, then what happens is that the point of contact will be always stationary. If that is not stationary, then this without slipping will not work. That is why this without slipping is important. So ultimately, what is your conclusion is that the point of contact of the rolling object, in this case a sphere, is not moving. Okay, that means, how do you say that it is not moving is that its velocity is zero. So we can say that the velocity of point of contact, velocity of the point of contact is zero. The velocity of the point of contact is zero. So what is the meaning? The meaning is that the equation of the constraint has velocity. So this is what is the point that you have to catch. Let me go back here. You see this? You see this one, q1 dot, q2 dots. These are speed or velocities. That is what you have to note down. If the equation of the constraint means f means a functional relation. If the equation of the constraint contains the velocities, then the system is classified as non-holonomic. So that is the reason. So we are asking the question, give me the reason why you classified it as non-holonomic. That is what is the question. The answer is that the equation of the constraint is going to contain velocity, because we are saying that the speed of the contact point is zero. Not moving means what? When you say stationary means not moving. Not moving means velocity zero. So finally we are trying to say that the equation of the constraint f of whatever you write, then comma q dot is there, because this particular velocity is entering into picture. And because of that reason, we will classify this under the non-holonomic case. So like this, we will be classifying whenever a particular problem is given. Okay, there is nothing much to work out here mathematically, but it is only a proper classification, whether velocity is appearing explicitly, time is appearing explicitly, or certain things are absent. So based on that, we can classify into holonomic and non-holonomic system. Now that we have seen that the velocities are entering into picture, the next question naturally comes is, what happens if time is explicitly present and time is explicitly absent? So this is also another interesting point. The equation that we are already familiar, namely the one with the simple pendulum, x square plus y square equal to L square, is the equation of constraint for a simple pendulum. And you see that this particular equation, we write that f of q1 comma q2, because q1 is x, q2 is y, and there is no t, so time is absent. What about q dots? q1 dot is absent. There is no q1 dot, not there. Similarly, q2 dot, it's not present. So velocities are not present. What about time? Time is also not present in the equation. X square plus y square equal to L square. Time is also not present. Therefore, we say that this is the equation. So this is a special kind of constraint equation where the time is not explicitly present. So like this, there are many situations, or in many cases this will happen, and therefore there is a further classification of the constraints. And this particular situation, whenever the time is absent or whenever time is not explicitly present, then those constraints are known as scleronomous constraints. The opposite of this scleronomous constraint will be the one where t is present. So the next option would be like this. If t is, or instead of saying if t is, I will write down like this. If the equation of the constraint depends on time, that means t is now visible. It depends on time. Then This is the exactly opposite to the scleronomous constraint, and the name is the Rheonomic. So let me write down that. Rheonormous constraint. So these are the basic classification apart from the previous one. The previous one means so whatever we have discussed up to the last the previous board, where you bring the velocity into the discussion. So here it is. So where the velocity. So when the velocities are present, you again classify it as non-holonomic only, but you don't give further new name. But whenever the time is present and when the time is absent, then you further classify. So what is that you are further classifying is you are classifying the original holonomic system into further division. So remember therefore that the scleronomous constraint and the rheonomous constraints will be further classification from the holonomic. So both of them are holonomic. So you can always say that let me write down like this here. We can have the holonomic constraint, that is fine, but within holonomic, because you know already that for the case of the simple pendulum we have holonomic only, so that is okay. So within holonomic you make further classification into scleronomous or rheonomous. That is what we mean to say. Similarly, for the case of non-holonomic system, once again you can tell whether it is scleronomous or rheonomous depending on time, if t is present or t is absent. So in order to demonstrate this is clear to you, scleronomous is clear because whatever equation that you have for the simple pendulum straight away come under that category. So you don't have to worry. But suppose if you ask the question, how do I understand a rheonomous constraint which is still holonomic? Because holonomic is the one where we have the equation of the constraint is well known, the equation of the constraint is equal to 0, the equation of the constraint does not contain velocity, all those conditions are satisfied, so that is why it is holonomic. But now you are bringing another difficulty where time enters into picture, and therefore it is known as rheonomous. So how do you understand a rheonomous system in reality? Is that it's a quite simple one. What all you have to do is that you take a simple pendulum like this. You have this particular thing, that you take a simple pendulum apparatus, and then so this is how you have the configuration for the simple pendulum. And in order to understand what is Rheonormous constraint, you have to focus your attention to this particular point of pivot. So what is the point of pivot here? So point of pivot is this one. So let me show in some kind of yellow color here. So this is the point of pivot. Now, usually when you are going to do an experiment with simple pendulum, what is the point of pivot? Will it change when the pendulum is oscillating? Will this point of pivot also change its position? No, right? So this is the bob. So the bob is there. So the bob executes oscillation like this. So that's fine. Now the question is, what happens to the point of pivot? Point of pivot will not change with respect to time. So if time changes, this particular fixed point of pivot means it is a point which is fixed. That point will not change. Now you consider another example. So this is very clear. So this is the example of a clear scleronomous system. Okay. So that is perfectly okay. Now what is that we want to know from the Rheonomous system is very simple, that you have to, that is you are there now. What you do is, in your hand, now you carry this particular simple pendulum in your hand. So you have a pendulum like this and then oscillating, and then you are walking. So you walk now. So you take the pendulum and you keep walking, and the pendulum is oscillating as usual. Now what will happen? Now will you classify it as scleronomous or rheonomous? That is the question. So that is a small change. So what happened is the point of contact here, whatever I am talking about, point of contact is now in your hand here. And you are not standing in a place. You are now moving. See, you are walking now. Now when you are walking, what happens is this point of pivot is also moving. That means the position is changing. That's what I mean to say. Therefore, the position of the point of pivot is also changing with respect to time. Oscillation takes place, that is going on as usual, but however the oscillations will be affected because of this particular point of pivot when it is changing. And therefore now the equation of the constraint will not be as simple in the earlier case. In the earlier case the equation is very simple, that you have an x square plus y square equal to L square. But now once you started to move, for example, the moment you started to move, then the equation of the constraint will not be this, it will change. So maybe how does it change, that depends on how you move, but for the time being we can write like this: x minus x naught into v. V is the speed, at which you are walking. Suppose if you are walking at a speed of v, and then we can say that the coordinates can be calculated. Maybe instead of x naught I will write like this: v naught is a constant speed, then you have a t, so at that speed you are moving, then you can write down the whole square, then plus y square. Why nothing happens? So basically, you are not going up and down, you are going to walk on a level surface. That's the meaning. If you are also climbing up, then y also will change. So let us assume that you are only making a movement in the horizontal plane, so that it is x minus v naught t square, that will be equal to L square. The other things won't change. So this will be the equation of constraint. So this equation of the constraint will have a time entering into picture. Now here you have to be careful that you should not think that velocity is entering into picture. No, it is not so. Basically, this is some constant speed. So it is a constant speed that you are going to have. So it will not be considered as velocity. It's a number. At some constant speed you are moving. So it's a number. So mathematically it is a constant. So there is nothing like x dot. You can't write x dot for that. So there is a constant value. And what is important is that t is entering into picture. So that means at various times the position of the pendulum itself will be at a different location. That's why t has to enter into picture. And since the equation of the constraint has the time here, we will classify this under the Rheonormous constraint. Similarly, various options are possible. Instead of you holding it and going to a different place, you can attach a vibrator. For example, you take a vibrator. So the vibrator goes to left side and right side. It vibrates like this. You have certain mechanical system which vibrates like this. And then you bring a simple pendulum and attach it here. So that is where a simple pendulum you attach here. And then it is as usual, it is going to oscillate, that's fine. But I am talking about the point of pivot. Now the point of pivot is here, and then you are now switching on the vibrator. Then what will happen? The whole pendulum will vibrate going left and right like this. So when it is happening like that, how will you write down the equation of constraint? The equation of the constraint will be something like this: x minus, we can say that some x naught into cos omega t. That is, it is going to vibrate harmonically. Let us assume that some harmonic execution is going on for the vibrator. Then we can write like this. Then plus, and the y direction we don't change anything. In that case, then we simply write down plus y square equal to L square. So this is the equation of constraint. And once again, you can see that because of the presence of time here, we will classify this particular system as Rheonormous system. So we can classify the dynamical systems into major categories, namely Rheonormous, scleronomous, then we have holonomic, non-holonomic. These are the main classification, and the formal way of writing down would be in terms of f of. So we can that's what I have been telling in the last few minutes. So you must be in a position to write down like this. This method, either this way or this way, and so on, or this one. So the general ways of writing down the constraint is one of the important things. That means I'm talking about some kind of competitive examination where they will give the appearance of the equation and you have to tell what is the classification. So you must be able to distinguish whether q dots are present, whether t is absent. That is what you have to search to get the answer. There is nothing to do calculation here, okay, for the classification purpose. Okay, so once you have learned these kind of terminologies and classification of systems, now this one would be much more familiar to you, namely the conservative system we are going to see. And basically, right from your BSc, you must have learned what is meant by a conservative mechanical system. Is the same definition, of course. The definition is that whenever the force acting on the system is expressed as gradient of a scalar potential, then it is known as conservative system, otherwise non-conservative. So it is the same definition that you learn in your BSc, which means that basically you write like this: if the force acting on the system can be written down. So the condition is if is there, not always. If the condition satisfies, then it is conservative. So how do you write that? Is if the force can be written down as the gradient of, so gradient 3-dimensional is gradient. If it is 1-dimensional, simply it is the first derivative of a scalar potential. So scalar potential can be written by either V, generally capital V will be written, or phi. So if this can be written, of course here plus minus is not important. This plus and minus is arbitrary, depends on how do you define the location, or how do you define the zero of the potential. So you first define what is zero of the potential, and then from there you keep your potential measurements. So that is going to fix whether it is plus or minus. Okay, in the case of the electromagnetism, you must have studied that minus will come because we fix the electric potential to be zero at infinity. That is the reason. So in the case of mechanics, you have to fix which is the zero of the reference point, isn't it? So let me explain otherwise. See, suppose if this is your ground floor and this is your first floor. Now what happens is, if there is suppose let us say there is a ball here. One fellow has thrown the ball up here. So now at a particular time you take a photograph, the ball is at this particular height. So then you ask the question, what is the potential energy of this ball? So what is the answer you will get? The answer will be like this. A fellow who is standing on the first floor will say that the height is small h. That's what is written here. The height is small h, and therefore he will say that the potential energy is mg into small h. Whereas the fellow who is standing on the ground floor, what will happen? So for him, the height is this. So he will measure the height of the ball to be this much. So this is a different value. So he will say that my height is capital H. This is my ground level. So the person who is standing on the ground floor will say that the potential energy of the same ball is m into g into capital H. As you see, mgh and mg capital H are not same, isn't it? So because of that reason, this plus minus will come into picture. You have to fix which is zero level. If you say that the person who is, if you say that the zero level has to be measured only from the first floor, if this is the zero level, if this is the zero level, then anything that you measure below the zero, this is negative value. This is negative because this is zero level. So from here you are going to measure down like this until the ground floor. So whatever value that you measure will be negative value. So that is why negative values will come here. So plus and minus, that is not important. Okay, so that depends on the reference point. So the point right now, what is required for the case of the conservative system is that whenever the force acting on a particular mechanical system can be written down as a gradient of a scalar, if it is possible, if this condition is possible, or if the equality is valid, then we classify that particular mechanical system is a conservative system. But here now we are going to put some additional conditions here where the phi is a scalar function. That's fine. It has to be a scalar. Otherwise, you can't take gradient. So phi is scalar, that's fine. But phi will be only dependent on the generalized coordinates. That means which is absent, I will tell you, and q dot and t are absent. This is important. So this is the reason why I am explaining now. Okay, usually conservative, you know already, definition is also same. But what is that you are learning extra now is that the scalar function should be a function of generalized coordinates only. That only is important. If it is depending only on the generalized coordinates, then what will happen to the generalized velocity and time? So the generalized velocity and the time will be explicitly absent, or it will not be present. If it is not present, then we will classify, it's a classification, we will classify that the system is a conservative system. So naturally the next question comes, okay, now the scalar potential is not at all independent of this one, they are all present, then what will happen? So the other case is this. So other case is this particular function phi, as usual, it depends on the generalized coordinates, but in addition, now what happens is it depends on the velocities or time. It can be both, or it can be any one of them, q comma q dot or q comma q dot comma t. In any case, whenever you are going to have an additional dependencies like that, if it is explicitly present, then instead of conservative, we will use another name, and that is known as, the system is known as monogenic system. So this particular terminology is important. So whenever a new term comes, you will be having an opinion that, okay, you will think that something new and you don't know anything about that. It is not so. You already know conservative system. So it is the same conservative system, but you bring the q dot and t also into the equation for the scalar. This is the scalar potential. Potential means potential energy. When you are going to consider this kind of height measurements, and then you are throwing the ball vertically up, the potential is basically gravitational potential. So if phi is the gravitational potential, and if you take the gradient of that, I will be getting the gravitational force. This is the gravitational force. This is the gravitational potential. That is what it means. So, and you know that this is a scalar quantity. So we write that this is scalar potential. So our conclusion is simple. Let me make the conclusion. Whenever the scalar potential depends on velocities and time, then such mechanical systems are known as monogenic system. And in a much special situation where if the scalar potential depends only on the coordinates, okay, only is important, only on the coordinates, then that particular system is known as conservative system. In any case, you must be in a position to write down f equal to gradient of phi. Otherwise, completely it will be non-monogenic and non-conservative system. Of course, you know what is non-conservative. If f is not equal, if you remove the equality and put a non-equality here, then it becomes non-conservative. So that is quite natural. So for the time being, the discussion is on the definition of the monogenic system. Monogenic system means forces are derivable from. So maybe we will write this particular word. I'll say forces are derivable from scalar potential. So the derivable from means, that is what we mean to say equal to gradient. You can derive it just by taking the first. This is the, if you do per this differentiation, you can get the force. That is called derivable. Okay. So these terminologies are somewhat important. Otherwise, without knowing the classification, you also don't understand what to do with the equation. So now you know the classification. You have an idea about the general appearance of the equation of constraint and so on. Okay. To learn about the Hamilton's principle, first we need to know what is meant by a phase space. It is, everything is given in a different terminology. So that's why I would like to write in both ways. Okay. Whether you call it by the name phase portrait or by the name phase space plot or phase space diagram. So they are all very similar terminologies. So the main thing that you need to know is the meaning of the phase space. That is what is required. Once you have the clear meaning about this, we can proceed further towards the Hamilton's principle. So the meaning of this particular diagram, finally you understand that it is some kind of plotting. Okay, it is what is known as portrait, means it's some way of representing the same data in a different style. That's what it is. So what is that you are going to plot is that whenever a dynamical system is there, certain object will be located at a particular location x. Let us consider one dimension. In one dimension, the object is located at the position x. That's fine. At what time? At time t. So I'll write down that at time t. At a particular time t, the object is located at x on the x-axis. Not only that, since it is moving, it will have its velocity x dot. Because x, you can't derive x dot. You should remember one thing, that you can't obtain x dot independent of x. Whatever object is moving can have its own velocity. Just because you know x dot cannot be calculated from numbers. If you have equation, it's a matter of derivative. But if you have a number, when you are performing an experiment, when something is moving on the x-axis, I will tell you that at time is equal to 5 seconds, the location is 7 meter. That's all I will tell. Can you tell what is the speed? You can't tell anything about the speed of the particle. No way you can get. So that is why x dot should also be measured at the same time. So the fellow who is measuring at time t equal to 5 seconds, same fellow has to measure what is its velocity. So that's what I am writing, that at a given time t, the particle is located at the point x. And not only that, at the same time, the particle's speed is x dot. So you are going to make a measurement and you are going to keep this data. So this is the data basically, and which means that you are going to have, if these three values are there, if you want to plot, basically what will you do is that you make a tabular column like this and say that at time t, let us say that 1 second, 2 seconds, 3 seconds, etc. What is my position? You fill this number here. So the position of the object will be like this and so on. And that's all. So this is one table that you have. Now using this particular thing t and dx, what you can do is you can immediately give a plot. So immediately we can say that you can draw like this. So this is the time axis is always horizontal. Remember, time axis is always the independent one. Therefore, it has to be plotted along the horizontal axis, namely the x-axis. And then the vertical one would be the one which you are measuring, isn't it? So what is that you are measuring now? Position. So position is represented by x here. So remember, this x is not x-axis. So you have to be more careful. This x is, whatever that you have written down here, is not the x-axis. This is position measurement. Okay, not the x-axis. Okay, so once you have the table, you can always take this set of numbers and then you can plot whatever thing that it comes, you can plot. This is fine. You got a number. So that means you have taken x here, you have taken t here. But what happened to x dot? The information about the x dot is missing in this graph. Now, since the information about the x dot is missing in this graph, what you do is you make another table. So which means that you make a very similar table like this. And in this table, once again you write the time here, and instead of x now you write x dot. But this time is identically same time that you have here. So if there is a 1 here, means here also 1. Same 1 should be there. If here it is 2, means here also 2. Whatever time is there, it is identically same time. So that is there. And for these times, what are the speed here? That data is there here. So you make a table like this. And then from this particular table, you draw another graph. So this graph, what will happen is the x-axis will be as usual. The t will be the x-axis. And now the measurement data is the speed. Therefore, I'll say x dot now. So that is the speed of the particle. So now based on this, you can always plot whatever curve that comes here. So this curve will not be the same as this curve. That is going to be a different curve because it is going to have different speeds which has no connection with the position of the object. So therefore you get two graphs. So remember, finally what you have is you have two graphs are there. So understanding the information or understanding something with two graphs is sometimes considered difficult because things are happening at same time. You see, whatever the time axis that you have here is identically same time. So the question naturally comes, why should we repeat the time axis two times and make two graphs? So question comes, can we not combine these things into a single graph? That was the question, and the answer is yes. You can combine by eliminating two times. You are making the time axis here, and that can be eliminated, and we can make a single graph. And the answer is finally whatever graph that you are going to get is known as the phase portrait. That's what is the ultimate answer. The answer is, if you are going to combine these two graphs, you're going to combine them, then the graph is known as the phase portrait. So the question is that how are you going to combine means you are basically drawing a graph like this, in which this will be the x here, which is the position of the particle, and on the y-axis you will be having the speed of the particle x dot. This is x dot, that is the speed of the particle. And that's all. Once you have this, you will maybe having some kind of a graph like this. Some graph you may get. And then what is some graph you will get which is not very similar to that. So the interestingly what happens is the appearance of the graph, namely the present graph, will be quite different from the graphs that you have in the two independent one. You see the appearance, this one. This is your x versus t graph. This is x dot versus t graph. These two appearance will be quite different from the graph that you are going to get. This is x versus x dot graph. So this is the distinction you just take care. This is x versus t graph. You will get a different style. The appearance will be very different. And in this graph, interestingly, now you have to be careful and ask the question, in this graph, x is present. Yeah, it's present here, x-axis. And x dot is present in y-axis. That is fine. But where is time? Time is not visible in this particular graph. So t is not at all there. Then you think that how this is correct. So the answer is that it is not that time is disappeared. It is there. So where is time means time is there, but it is not visible to you. So to know that time, actually, this is the point that you have to remember, that when you are taking the first one, that is the one you have taken, right? I am making a round here. So this is the first time. First time doesn't mean one. Okay, whatever be the first time that you have, usually t equal to 0 second is how you start the experiment. So that point will be, you first specify like this in this diagram. Like this, you have to specify a point. That means that is the point corresponding to the starting of your experiment. And after showing that point, you have to put an arrow. Once you put one arrow, that is enough. That means the other arrows are naturally this is coming. Which means that this arrow is going to tell you, this particular arrow is going to tell you increasing time. So increasing time means that is what we say evolution. Time evolution of a dynamical system. What is the meaning? Time evolution means when time is increasing, time will not decrease. Time will always increase. So when the time is increasing, how the dynamical system will evolve. Evolve means some kind of changes are there in the system. What are those changes? So those changes are basically the position is changing and velocity is changing. That is how evolution takes place. Evolution means what is changing there? Changing means position is changing and speed is changing. How the position and the speed is changing as time increases. That is exactly this graph. So in this graph, where is the time? That question now, it is now clear. Time is present. The starting point will be, if you can always represent that this is the starting point. That means it is initial condition. Okay, this is how I am going to start the experiment at time t equal to 0. And once time is increasing, then the values taken by the system are now shown by this particular plot or curve. So this is what is known as a phase plot. Phase space diagram. A plot between x and x dot. So what is meant by phase space is a plot between x and x dot. So such a plot is known as phase space plot. So this is important. Phase space, what is the meaning? Phase space means it's a collection of data where the data is x versus x dot. That's all. Of course, as a function of time is there, but time doesn't explicitly visible there. But in the form of a data or in the form of a tabular column, you have time that is there. But however, the set of data taken by x and x dot is what is basically phase space. And here this is very important because we are now moving into a space which is away from the usual three-dimensional Euclidean space. I am saying it is important because there is a word here, space here. You see this one. So this one, this space is not the Euclidean space. So Euclidean space means what? Euclidean space you already know. That is the space in which you are living. Okay. If you ask where is my pencil is located in this particular space. That is the space. Physically, it is, you can see, you can feel, everything is physical. But that is not the space. I want to emphasize that the space written in here, in this particular here, phase space, that is not the physical space. Then what it is? So that is what I would like to tell. But rather it is a mathematical space. So the distinction between the physical space and the mathematical space is very important. Because usually when it is not explained, you think that it is some kind of, you have to imagine as if there is a space like that. Okay, it is not like there doesn't exist any space. Okay, in the real life. In mathematical space it is there, but you can't see. So why do you want to use the word mathematical space is that mathematical spaces are the ones that cannot be seen. You can't see, you can't feel. Physical spaces, yes, you are existing in physical space, so you know. So by that, what do you mean by mathematical space? Let me give you an example to get a feeling. I'll show you an example here. This is a number 1 that you have. That's fine. Now what you are asking the question is that show me where is 1. This is the question that you are asking. You know that 1, 2, 3 numbers are there. You know that numbers exist. 1, 2, 3, 4. That is fine. But you are asking the question, you show me where is 1. I want to see. You show me that. But the answer is that you cannot write like this. You cannot write like this 1 and then see this is the place where I have written. That is not the answer. This is the place where you are writing, but this is not the place where 1 is present. So you must be able to capture the distinction. So you are basically asking where is 1 and you show me that. Can you show it? You can't show because you don't know where 1 exists first of all. 1 exists, that is clear, and you are writing 1. Okay, you are writing 1 here, you can write 1 here, you can write 1 here, you can write 1 here. That you can do. But first of all, where was the 1 originally located? Can you show me where is the location of 1, where it exists? The answer is you can't show. The reason is the 1 is existing in mathematical space. Mathematical spaces are the ones which are not visible. You can't feel it, but they exist. So the concept is very crucial because this is the place where people get a confusion with visualization. You don't have to worry. I want to visualize 1, 2, 3 means you can't visualize. 1, 2, 3 are the numbers that exist in mathematical space, but such mathematical spaces are not visible, and therefore there is no point in asking the question I want to visualize. So therefore I would like to make this point clear that anything that is mathematical cannot be visualized directly. You can represent it somewhere in a physical space, and that is what you can see. Okay. So therefore, let this point be clear before we proceed further. Yeah. So once again, coming back to this concept is very important, namely the mathematical space concept is very important, and therefore the phase space is a mathematical space. Basically, it is a number x comma x dot. So it is basically x comma x dot table. That's fine. This table is what is visible to you after writing. That concept should be distinguished from this graph. See, you will get more and more doubt. Now you'll ask a question. This particular phase plot or a phase based diagram is visible. I have drawn it and shown it is visible to you. How can you say that phase space is not visible? So that is a place where I am trying to explain. You take the numbers and then show it on the physical space. So remember that when you draw the x-axis and horizontal and y-axis on the vertical, that is drawn on a physical space. That's why you are able to see. Okay, and you can draw one more axis. You can draw. That's all. At the maximum, you can do that. You can draw one more axis and then take another data. That is only true. You are trying to visualize some part of that by plotting it into an Euclidean space. But that doesn't mean that the entire mathematical space you are seeing. That is where you have to be careful. So the set of all values which are written down in the tabular form, that is set of all values. Okay, all values is very important. It is not a small data. You can have infinitely large data, for example. Okay, such big set of numbers is what is known as phase space. Set of number, ultimately it's a set of numbers. That's all about it. So once you say it is set of numbers, yes, it is there in mathematical space. If you want to visualize something, you take a few of them and then draw it on the Euclidean space. You have to draw it on an Euclidean space, and after that, that is what you are seeing. So therefore, the distinction between the Euclidean and the mathematical is very important for further discussions. So having seen the detail or the distinction between the Euclidean space and mathematical space, we move on to the concept of the trajectory. Here is the place where the requirement of mathematical space becomes important. Okay. Usually what happens, trajectory, of course, by the terminology is simple as long as you live in 3 dimension, but when you move further, you will be knowing the difficulty. The trajectory, or you can say curve, usually we say it's a curve, for example, and anything that you plot. Suppose in the simplest situation of the x and x dot, you have taken a plot like this and then you have shown some kind of a plot. Let us draw a simple diagram like this, and you have the starting point of the experiment, and then time is changing. When time is increasing, this is how the data looks like for the x versus x dot. So this is the phase space diagram. And here I am showing a simple example where the phase space diagram looks like a circle. And this particular circle is what is known as a trajectory. This is known as trajectory. But however, things will be simple as long as when you have one-dimensional situation. This is for one-dimensional situation. So you have only x and x dot. You have a tabular data x and x dot. You took a graph paper and then plotted. So taking a graph paper and plotting means you are basically plotting on Euclidean space. So in the next class, we will see how the simple concept of the trajectory or a curve will get a complicated situation, and we are going to call that as a manifold.